Problem number 27 in group theory. Prove that if H is a subgroup of G of finite index, then there is a finite index normal subgroup of G contained in H. Okay. Suppose that H is a subgroup of G and it has finite index in G. So we'll write that like that. Okay, and we're going to consider the left cosets of H in G. So the set G modded out with H, which is equal to GH, such that G is in G. So we're going to consider this set, and we have that G acts on G modded out with H by left multiplication, giving a homomorphism phi from G to the symmetric group on n cosets, where Sn is the symmetric group on n cosets. Okay. We're going to let n be the kernel of our map. We know that n is a normal subgroup of G. So it just remains to show that n is contained in H and it has finite index. Okay, so we're going to pick an element in n, then the image of that element, so the image of something in the kernel, is the identity permutation. The identity permutation on G modded out with H. Hence, GH is just going to give us H. And we have that GH is equal to just GH. Thus, we have that GH is equal to H. And so G is in H. Okay, so we have containment. Now we just want to show that it has finite index, and so we're going to invoke by the first isomorphism theorem. We have that, let's see, we have G over n is isomorphic to the image, which is a subgroup of Sn. Considering orders, we have that, okay, G modded out with n is the same thing as the index of G and n of the order of G modded out with n, which is equal to the order of the image, which is less than or equal to the order of Sn, which we know is equal to n factorial. Let's compile this. So we're saying that the index of n in G is less than or equal to n factorial, hence it's finite. Therefore, n has finite index in G. So we've shown that it has finite index, it's a normal subgroup because it's a kernel, and it's contained in H. And so we're done with 27.